Hello, everyone, and welcome. My name is Rula Deeb. I'm principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to develop forensic methods for PFAS source tracking and allocation. The webinar will feature two speakers. First, Mr. Jared Dragland from the National Institute of Standards and Technology will discuss his work on the development of an open source database infrastructure for the storage and management of chemical information, analytical method metadata, and consensus mass spectra. Second, Dr. Jens Blotvogel from Cicero in Australia will talk about his research to identify products and source-specific marker compounds that can be used for forensic investigations. He will also talk about his efforts to develop analytical methods that will be exportable to more widely available, lower resolution mass spectrometers. Each of the two presentations will be followed by a brief Q&A session, and if time allows, we will conclude the webinar with a longer Q&A session. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you can view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slides or if your screen freezes, try keying in Control and F5 to perform a hard refresh of your screen. If you're accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, just call into the conference line shown here. You can also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for our speakers. And in case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Note that we will be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. So this is another way to follow today's proceedings. The broadcast will be listen only. You can submit questions using the Q&A box on your screen. Please don't wait until the Q&A period to submit your questions. Get them in well in advance of the Q&A session so we can start lining them up. We do ask that when you submit your questions to add your organization name at the end of your question so that we can identify it during the Q&A session. The next few slides provide a very quick overview of SERDP and ESTCP. SERDP is the Strategic Environmental Research and Development Program established in '91 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which innovative environmental and energy technologies are demonstrated. These investments capitalize on past investments under SERDP or other research programs and are really designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with most of the SERDP research occurring at the lab and pilot scale, with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are several environmental drivers for the type of work funded by SERDP and ESTCP with the underlying objective of sustaining DoD ranges, facilities, and operations. This is a broad undertaking that takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, unexploded ordnance and munitions constituents, as well as other environmental drivers. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contamination from past practices, including impacts to groundwater, soils, and sediments, UXO contamination, and developing management approaches for contaminants of emerging concern, like PFAS. The second part of this is pollution prevention, with a focus on eliminating chemicals of concern or hazardous materials in manufacturing, maintenance, and operations on military installations. We have several main focus areas for research and demonstration at SERDP and ESTCP as shown here, with PFAS and AFFF being one, and that's the topic of today's webinar. As mentioned earlier, technology transfer is very important within both programs. Technology transfer efforts include the development of videos, training workshops, and guiding documents. This webinar series is a substantial component of our technology transfer efforts. The webinar series highlights research and demonstration efforts from all of SERDP and ESTCP's program areas. Today's webinar is the last one for the year. Registration for 2024 webinars will open next week, so please make sure to check in and to register for upcoming webinars. Note that we're kicking off 2024 with another PFAS webinar, so please stay tuned. You can find additional information about upcoming webinars at this link. Note that this link also works to access older webinars, which are all archived and can be viewed at this link. So you can go back and listen to recordings of old webinars, download PDF of all the slides back 10 years when we started this webinar series in 2014. So with that, we're going to go ahead and get started. It is now my pleasure to introduce our first speaker, Mr. Jared Regland, who's a research biologist at NIST, working at Hollings Marine Laboratory in Charleston, South Carolina. Jared's focus in the Chemical Sciences Division includes developing strategies for scientific data management and implementing lab information management systems, and also developing tools, data tools for environmental metrology. Such data tools act as workforce multipliers, reducing sources of human error in complex calculation, accelerating the data processing tasks, and providing rapid insights into complex data. Jared's past research interests include physical method development and quantification of a wide variety of legacy and emerging organic chemicals in the environment, including PFAS, as well as fundamentals of mass spectrometry. Jared holds a bachelor's degree in biology from Tennessee Technological University and a master's degree in marine biology from the College of Charleston. Jared, we're delighted to have you. Please proceed.
Thank you for the introduction, and thank you to all who've joined us today for your interest, and thanks especially to my co-investigators on this project, Drs. Benjamin Place and Jessica Reiner, also at NIST. There we go. I'll be giving an update today for project ER20-1056 about improving access and utility of data. So we'll start with some background about the project, discuss the portable database infrastructure that's been put together to support that, and introduce you to some of the tools that are included. I'll talk briefly about the upcoming interlaboratory study that we'll be conducting in 2024, and then wrap up with conclusions and benefits we believe the project will provide. The entirety of chemical space is almost limitless, and for a subset of that, we know the mass spectral properties either of through empirical libraries or computational methods. Purified mass spectral standards, however, only comprise a tiny fraction of that space. So to confidently identify analytes outside that space, there are two main techniques using mass spectrometry. Suspect screening analysis uses a predefined library of analytes, either empirical or theoretical, and can be used to identify portions of the known analytes. For everything else, non-targeted analysis attempts identification with no a priori knowledge of contents using a variety of informatics techniques. NTA is, however, unavoidably still very labor intensive. Academic, governmental, and industry laboratories often then build up and produce their own in-house mass spectral libraries. This gray data is often of very high quality, but limited use outside the laboratory producing it. Despite this, it can quickly become siloed and is often incompatible between labs due to different workflows, which makes sharing of gray data much more difficult. ER 201056 is an effort to make that a bit easier by creating an infrastructure for portable databases where metadata are tied to mass spectra, recording instrument settings and sample properties to assist with interpretation. One goal is that these databases can then be used across research groups with the toolkit to increase interoperability and reusability. Work started on ER 201056 in late 2020, and I'm happy to share that version 1 is available today. It supports both non-targeted and suspect screening analysis for high-res mass spectral data. The DIMSpec toolkit uses only open source tools, and the first DIMSpec database contains mass spectra for PFAS. For context, this is a distributed code-based project intended to supplement existing SSA and NTA workflows with empirical data. Standard disclaimer: NIST-developed works of this kind are provided as a public service, and as such are expressly provided as is with no warranties, and any mention of commercial products are intended for information only and does not imply recommendation or endorsement by NIST. There are 5 infrastructure elements intended to operate in a cyclical reinforcing pattern. We're attempting to provide a capture and sharing mechanism for gray data to expand the sphere of known analytes. Those elements start with analytes of interest. For this effort, we seeded the first DIMSpec database with the NIST suspect list of possible PFAS, which includes almost 5,000 curated PFAS structures and includes unambiguous machine interpretable identity for each PFAS. Data population routines support both open source and proprietary formats through a pipeline we've defined as part of the project. Instrument output is translated to the open.mzml standard, and metadata for chromatographic peaks of interest are annotated using a fillable template called the Non-Targeted Analysis Method Reporting Tool, or NTA-MRT. From 104 samples from various sources, we've identified and characterized 132 distinct PFAS, represented by over 350 chromatographic peaks, from multiple instrument vendors operated in multiple modes and settings. Spectra were collected across each of those chromatographic peaks to build consensus or uncertainty-based mass spectra. Each scan is recorded in the database. There's always a bit of variability in both the mass to charge value and relative intensity across these peaks, and DIMSpec respects that uncertainty. These uncertainty spectra are then used by the toolkit to match new data against the library, and we can provide an uncertainty range around the resulting dot product rather than giving a single value. We've implemented a few performance enhancements for the database search. The first of those is a reduction in data size, which allows the database file to remain small, which is important for portability purposes. By extracting only relevant portions of a chromatogram and leveraging the inherent data compression of the SQLite database engine, we've reduced about 13 gigabytes of MZML files for this data down to a database file of around 50 megabytes. That means that the file can be shared easily, even through email. Search is supported for both MS1 and MS2 levels for now, but DIMSpec is capable of supporting MS to the N if necessary with some refinement. Dot product scoring is returned for all relevant levels, and performance is increased using simplified view facilitated searches. That gets us to a full analysis toolkit, which wraps all the functionality to create, iterate, and refine databases for any use case. This is not limited to PFAS, although that's where we started. As it uses only open source tools, in this case R, Python, and SQLite, it's endlessly extensible and should fit easily into existing data analysis workflows. The goal is to use the toolkit to identify and characterize new analytes, which then become analytes of interest, and supporting data imported back into the database for immediate use. It includes programmatic support through an application programming interface, and use cases are simplified by inclusion of, for now, 3 web applications. I should note, the project is built from the ground up to be completely portable and can be used on workstations without an internet connection. The network hosting is fully supported. To add value to existing workflows, we've attached an application programming interface, or API, to the database. This allows developers and data managers to extend and complement existing workflows and is easily extensible as development needs require. This is powered by the Plumber package in R, and that in turn powers the web applications that are included with the toolkit. A RESTful API is a way of machine-to-machine communication, issuing a query and retrieving data through URLs. The toolkit includes interactive documentation through Swagger as well to lower barriers to use. An example endpoint is here, where we're asking the database to return all data associated with compound ID 2627. The response is in JavaScript object notation, which can be read by virtually any software, and we can return that to an active data analysis session. The toolkit also includes a variety of convenience functions to build these queries more simply. This is the exact same request, returning data to an active R session. A common communication interface that allows us to quickly build web applications using the Shiny package framework in R. The first of those included in the toolkit is interactive documentation for the database itself. The next several slides are mostly screenshots from 3 web applications, and I'll briefly introduce you to each. Table Explorer is a simple web interface where users can select any entity in the database to get a plain language description of its purpose, the relationships it has to other entities, details about how to interpret each column, and a snapshot of the current data. This doesn't replace data management software, but it does make the database structure itself more transparent and easier to use. Combined with the API documentation, anyone wishing to develop on top of DimSpec should have all the tools at their disposal to do so. And we also include an application template to make it even easier to build on top. The second web application included in the toolkit is DimSpec QC. Here we have a simple interface that allows for quality checks of annotations for a given file. Users drop their instrument MZML file and a file in JavaScript object notation, or JSON, produced by the NTA MRT annotation workbook. A series of quality checks is then automatically executed for each annotated chromatographic peak. Here we've defined 7 checks, but these as well can be extended as needs dictate. The results of the quality control checks are then applied to the sample JSON files, and the resulting files are fit for import to DimSpec. This process doesn't filter based on the quality checks, since requirements may differ between use cases, but the results are still attached to the spectra alongside other metadata recorded in the NTA MRT, such as sample type and instrument settings. The third web application, Mass Spectral Match, is targeted toward the most common use case, identification and characterization in new experimental data. Here, users would load their experimental data to match it against analytes known to the attached database. Once a data file is provided, users can then identify the chromatographic peaks that they wish to examine. This can be done either by importing in bulk from an existing workflow, where you match up the column headers with what's expected, or they can be entered directly one by one. Each of the entries can be edited after the fact. After that, a simple button click allows users to process those data and continue to either compound matching for SSA or fragment matching for NTA. The suggested workflow is to identify compounds first, and if a match is not found, to proceed to fragment matching for characterization purposes. Selecting one of the chromatographic peaks of interest allows comparison against every spectrum held in the attached database. You'll notice that this is not just one result per analyte, but many, often with different context. There's a considerable amount of information here with the ability to switch between MS1 and MS2 match visualization and to switch on the fly the various matches to see how they stack up with experimental data. Context is important. And so every match returned in this table also has a method narrative describing how the reference data were generated. Because we've embraced mass spectral uncertainty across a chromatographic peak, we can bootstrap the match score through permutations to give a range of dot product results instead of a single value. This increases the confidence in the match score by providing an estimate of the uncertainty around that match. If a direct match is not found, the next step is characterization of fragments. DIMSPEC keeps a record of all past fragment annotations, and MS-Match uses that for automated fragment annotation to assist with characterization. Here, 3 major fragments were observed, and we were able to identify 2 of them with high confidence and structural notation. In our workflows, this has cut annotation time for new data considerably. In fact, the last third of PFAS data that are currently included used MS-Match for identification and annotation in our workflow. Continuing with the same fragment characterization, every fragment match is surfaced, along with a narrative around that match and the context for where else the selected fragment has been found. Similarly to compound matching, selections in the table on the left update all the information to the right, including which known analytes include that fragment and references to peak records in the database within which it was identified. That won't get you to an analyte identity, of course. This is just another example where we're providing context to improve confidence and leverage data for decision making. We can then dive more deeply into records for any given analyte or peak to retrieve additional information if necessary. So for compounds, we offer cross-linking identifiers to other data sources, such as EPA's CompTox database, as well as machine actionable identifiers, such as SMILES, INCHI, and INCHI Key that carry structural information. All of this is held within DIMSPEC. We can also offer some basic information about peaks, though we're looking at expanding this information. Again, DIMSPEC is context aware by design. We'll be offering DIMSPEC to participants in a 2024 interlaboratory study. Those participants will use their methods in-house to identify PFAS in 3 custom-made solutions that we've created at NIST, and they'll receive an anonymized performance report once the study ends. DIMSPEC is not a requirement for participation, but we hope to get some meaningful feedback on its performance and where it should be expanded. So in conclusion, version 1 of DIMSPEC is complete. It's available today on GitHub. It is an R project. It will take a little bit of familiarity with those types of tools for now. It includes the full toolkit, a comprehensive user guide as a webbook, and a database populated with high-res mass spectral data supporting PFAS identification and characterization. This is all open source by design, as I mentioned, to support extension and serve as a supplement, not a replacement, to existing workflows. Interactive documentation in the API should help data managers and programmers to build on top of it, and MS-Match is more of a bench-up tool for spectral matching and fragment annotations. We tried heavily to consider the use cases both for bench science and for developers who want to include this in larger workflows and expand out from there. That includes some exports as well to familiar library formats such as .msp. The entire DIMSPEC library for PFAS right now can be exported to an MSP if you use the NIST MS search. So to reiterate, we're talking about completely portable databases. These are one file and they require no hosting or network overhead, though we do fully support that if you wish to deploy this on your network for your organization. Because these are portable and small, distributing them between stakeholders should be easy and should provide for a common data storage and interchange mechanism. All you have to do if you are using the DIMSPEC toolkit and you receive a library from someone else is during the startup routine, point it at a new database. So distributing these between stakeholders should be easy, and the inclusion of machine readable notation throughout provides unambiguous identification of PFAS. We hope this mechanism for rapid annotation and identification confidence evaluation, as well as contextual transparency, increases the confidence for data submissions and sharing amongst stakeholders. So I'll leave you with a few resources for more information and end with a request. If you would like to know more or join the list of participants for the interlaboratory study, or perhaps more critically, if you have data you would like to contribute to the project, or if you would just like to take DimSpec for a spin, please reach out to us at pfas@nist.gov. DimSpec is intended to be a community tool to increase sharing and collaboration. And as part of that, we'd be happy to discuss data contributions as well as feedback about how the tool is working for you. So, thank you for your attention today, and I will turn it back over to our moderator. I went a bit quickly, so hopefully there's plenty of time for questions.
Thank you, Jared. Great presentation. Just a reminder for our audience, if you have any questions, please go ahead and get them into the Q&A box on your screen, and we'll relay them to Jared accordingly. We've gotten several questions already, so let's start with this first one. Can you remind us what PFAS data are included in the database?
Sure. Yeah, we have 104 samples. There are 83 analytical standards, 18 AFFF samples, and 3 commercial formulations that are in there. Those resulted in 351 identified analytical peaks, so chromatographic peaks. This is all LCMS data. We've recorded both MS1 and MS2 for those, resulting in over 24,000 individual spectra characterizing these. And those identify 132 distinct PFAS analytes at this point. Between the machine actionable identifiers and links to other external IDs, those PFAS are represented by almost 50,000 searchable aliases. The current DimSpec for PFAS database includes the entirety of the NIST suspect list for possible PFAS, which is almost 5,000. So we would love to be able to expand the representation of mass spectral data beyond what we already have. Of course, more data is always better.
Thank you, Jared. Have you presented your database development efforts to the appropriate folks at EPA? And what has their reaction been in the context of established analytical methods?
An analytical method in terms of measurements?
Yes, measurements and how you've, yeah.
Yeah. So I was just at CTAC in Louisville a few weeks ago, and I had some fantastic conversations with several folks from EPA. And so I think they will be giving this a spin soon. And they also have quite a bit of mass spectral data that they're considering which pieces and parts to contribute to this effort as well. So hopefully that will pick up soon in 2024.
Wonderful. This is from Max IR Lab, are there plans to extend this database from mass spec to other techniques such as FTIR?
Right, so the underlying setup of the database should be able to accept any XY coordinate data. For right now, the column headers are referencing things like mass to charge value. So there might be some naming differences that would need to be considered as part of development. But the underlying schema for the database should be able to accept any XY spectroscopy data.
Great. This next question is from the New Jersey Institute of Technology. Does the database also include some of the fluorotelomers, like the 6,2 or the 5,3 FTCA?
Yes, I don't have the full list of 132 in front of me, but FTOs are definitely included in there, as well as several other fluorotelomers and the standard actors that we're all familiar with. The majority of the 132 analytes that are currently represented in the database come from the PFAS 150 list. So.
Wonderful. All right, let's move on to a question here. Why the emphasis on context and disambiguation of identity in the database?
Yeah, so there is always this interesting thing that happens when humans start naming things. We look for shortcuts and commonalities, and that can really open you up in terms of chemical structures that are very diverse, like with PFAS, to misinterpretation. So if I'm using a particular acronym that makes sense to my lab, there's a lot of effort that has to go into communicating that to the community as a whole. The emphasis on disambiguation using structural identifiers as the basic identity is so that there's no miscommunication, no opportunity for misinterpretation of, say, a chemical formula that may have a variety of structures associated with it. And so that's why we've chosen to focus on machine actionable identifiers. Machine actionable identifiers are also key in being able to unlock chemical informatics because you're carrying that structure along, and it allows us to cross-link with different databases as well. So we've included aliases for EPA's CompTox database for all of the PFAS that are included in DIMSPEC for right now, as well as IDs for CAS numbers when we have those that are vetted with PubChem IDs, for instance, and the like. And the emphasis on context, the other part of that question, is instrument settings can at times result in slight differences in mass spectral properties. And so if you're measuring an AFFF and you're choosing a match hit, which is the most appropriate, you may want to only select for data that have only come from other AFFF samples, for instance, or you may have a slightly different mass spectrometer setting, whether it's collision energy or ionization energy or whatnot. And so we're surfacing that information to try to allow investigators to make the best choice for their particular context.
Great, thank you so much. Do you anticipate the number of PFAS in the database to increase significantly in the future?
I certainly hope so. That is our goal. Like everyone else, we had intended to do a bit more work, but this started in the heart of the pandemic. And so we would love as much data expansion as we possibly can. Again, we're hoping for this to be a community supportive effort that complements existing workflows so that we can communicate those back and forth.
Great, thank you. And one last question before we move over to Jens. How long will the interlaboratory study participants have to analyze the solutions and return the results to NIST?
Right, so recruitment for both the interlaboratory study and for beta testers for DIMSPEC should go out in January of 2024. Once the participants have been identified, we'll send out those challenge samples to them, and then they should have about 3 months to process and return those data to NIST.
Wonderful, thank you so much. We still have questions for you and we'll get back to them after the second presentation. But at this point, I'm gonna go ahead and introduce our last speaker today. Dr. Jens Blotvogel is a principal research scientist and team leader for environmental protection and technologies at CISRO in Adelaide, Australia. Jens also holds an affiliate faculty position in the Department of Civil and Environmental Engineering at Colorado State University in Fort Collins. Jens's research revolves around the fate of emerging contaminants, conducting laboratory and field scale experiments to elucidate both their transformation and their fate in natural and engineered systems. He has developed sustainable water treatment technologies, theoretical models for contaminant degradation prediction, and various advanced analytical methods with a focus on high resolution and accurate mass spectrometry. Jens has served as a principal and co-principal investigator for several SERDP and ESTCP projects on thermal and non-thermal PFAS destruction, real-time groundwater monitoring, and forensic applications. He received a master's degree in environmental engineering from the Technical University in Berlin and a doctoral degree in environmental soil chemistry from Colorado State University. Jens, thank you for joining us from an extreme time difference right now in Australia. We appreciate you joining, and please go ahead and start your presentation.
Yeah, thank you so much, Rula. And it's my pleasure to speak at this kind of unfavorable hour. At least it's Friday here already, so I only have one day left until my weekend starts. So to basically connect with the previous talk, Jared had in one way or another implicitly talked about high resolution mass spectrometry already and what you can do with these data. I want to delve in a little deeper here and talk about our method development in the area of high resolution or ultra high resolution mass spectrometry and how this is used for PFAS discovery and forensics. And we are using an instrument that's called FTICRMS. And so if you have not heard yet what FTICRMS is, then this is where my talk will start. So I'll give a brief intro on this very unique instrument. I'll be talking about data processing and confidence in the elemental assignments that we make and in the PFAS identification, basically. Then I'll give examples of applications in PFAS discovery and PFAS forensics, and finally come to conclusions. Also talk about our future work. So what you're going to see here in this presentation is the result of a 1-year limited scope project that just got extended for another 3 years to fully develop this method. And then I will conclude this webinar with benefits to the DoD and, of course, any questions you may have. So just to clarify here, what I'll be talking about is exact mass. This is something that we use to basically help us identify unknown PFAS, known PFAS too. But if you take a molecule, so I'm taking PFHXS as an example here, its nominal mass is 400 Daltons. Dalton is an atomic mass unit. However, the exact mass of this molecule is 399.94388. And so this kind of non-integer number is something that we can use for the identification of PFAS. And the reason is, or the source of this mass defect, as we call it, is in all the individual elements. So with the exception of carbon-12, all the elements and isotopes have a mass defect. And so in a elemental composition, in a molecular formula, if you add up all the atoms and isotopes to make a molecule, you get to some non-integer number, so to some mass defect that your analyte of interest has. And we can use that then to, again, identify the PFAS that we're looking at. So what we're using here is called FTICRMS, or in the long word would be Fourier Transform Ion Cyclotron Resonance Mass Spectrometry. It is, in terms of high resolution mass spectrometry, you may be familiar with instruments such as time of flight mass spectrometers or Orbitrap mass specs. The FTIC-RMS is the highest resolving of these mass spectrometers. It is, as you can see here, a pretty massive instrument, so it's quite unique too. There aren't that many of them around. The one you're seeing here is the one we are using. It's the world's highest resolving mass spectrometer, and it is housed at the National High Magnetic Field Laboratory at Florida State University in Tallahassee. And this is a user facility, so you can actually write a user proposal and get your samples on here. The problem is then that you're dealing with processing all the data that you're getting back. And so just to give you an idea of what that looks like, at the bottom you can see a spectrum that we recorded from a direct infusion dilute AFFF sample. You can see the very strong peak here at a mass to charge ratio around 500. So it's an electrochemical fluorination, AFFF, aqueous film forming foam, and not surprisingly, PFAS is the most abundant species here. And then we look at the first mass insert here on the top left side, and we look a little closer at the peaks, and we can see here the spacing of 1.9958 Daltons apart. So those are sulfur isotopes, 34 sulfur as opposed to the more abundant 32 sulfur. And we can use that for confirmation that our assignments are correct. And then when we zoom in more, and that's the top that I'm showing here on this slide, we can actually see two peaks here that differ in mass by the mass of 5 electrons, so 2.5 millidaltons roughly. These are 2 PFAS that you would have that would be unresolvable on, let's say, a time of flight mass spectrometer and even challenge an orbit trap. So if you have these close calls, you basically need FTIC-RMS to see that these are different PFAS to begin with, and then to start assigning elemental composition and create that molecular formula that you want to know what you're looking at. So this ultra high resolution, when we look at molecular weights or masses, that's a very strong line of evidence. We heard about time of flight mass spectrometers or high resolution mass spectrometers and a ppm error that is typically tolerated in the previous presentation. So for a time of flight mass spectrometer, typically we're hoping to be somewhere around 5 ppm error, maybe sometimes we get to 10. So what that means is, going back to our example of PFHXS, if you have a peak, in this case, in the example PFHXS, and you wouldn't know what this is, and you run it against a database of PFAS, it would come back with somewhere between 41 and 87 potential elemental formula. So you really would have no idea what you're looking at, or a really great large number of PFAS that you would have to choose from. An orbit trap mass spectrometer can get down realistically to a ppm error of about 1 to 2, and that limits the potential number of assignments for your analyte in this example to right around 10, so 7 to 15 somewhere. Easier to handle, but there's still uncertainty. With the FTIC-RMS, and I will refer to our initial publication at the end of this presentation, we believe we can get down to below a ppm error of 0.2. But typically you'll be looking at a ppm error of about 0.2 to 0.5. So then you have about 4 to 5 potential assignments in this case. For some of the analytes we've been looking at, we have an unambiguous assignment at this point, but here in this example of PFHXS, again, 4 to 5 potential formulas still for this analyte. So that means ultra high resolution accurate mass gives you a very strong first indication what molecule or what analyte you're looking at, but there is actually additional evidence that we need to collect from these mass spectra to unambiguously say this is the actual PFAS or the actual analyte we're looking at. So additional lines of evidence we collect from these spectra are, first of all, isotopolog abundances. I had mentioned sulfur isotopes already. So sulfur 32 is the most abundant sulfur isotope, but we can also see 34 sulfur, and we know the accurate mass difference between the two that we can look for. We also know the abundance of 34 sulfur, and we can use that when we look at the abundance of peaks that are spaced correctly. And then we can use other elements too, chlorine, for instance, 35 versus 37 chlorine, to help with the assignments. Another really important trick are Kendrick mass defect series, or KMD series. And so what you end up when you do these types of analyses, any type of high resolution mass spectrometry, is a spreadsheet basically, or a peak list of hundreds, if not thousands of peaks. So in the case of FTIC-RMS, we're talking about maybe around 20,000 hits per compound. And so the Kendrick mass defect then is an algorithm that is listed here that helps you sort your data and find series, in this case, that are related and that differ in mass only by the number of CF2 units. So with that, we can identify a whole slew of analytes as PFAS. So with that, we basically developed a workflow for this large list of peaks that we detect. And we identify these at a ppm error of 0.2. We do a suspect screening first. So there we basically run all the mass to charge ratios against the NIST suspect list that Jared had mentioned in a suspect screening. And we do isotopologue verification to come up with a list of what we call known PFAS. And then there are a lot of PFAS that are not known yet. So there we do a non-targeted screening. We have developed a database of potential PFAS and have optimized this over the years. The initial versions had to be run basically on a supercomputer. By now we can do these elemental composition assignments in about 10 to 20 minutes on a just regular standard laptop. Then do the isotopologue validation, and then look for these homologous series or Kendrick mass defect series, whether it's CF2 for PFAS or also CH2 or C2H4O series for polyethoxylates. All of that gives us a hint of what the composition of these analytes is. And then we end up with PFAS at different confidence levels, those that are known, those that are not known, and members of these CF2 series, or maybe individual compounds that are not members of CF2 series, where we have very little confidence in what they actually are. So we tried this initially on an aqueous film forming foam, but we also tried it on groundwater. So you can see my former team here at Colorado State University, my former institution. And then what I'm listing here are the detections we had in electrospray ionization mode, both in negative and in positive. And so in negative mode, and this is published in the AFFF sample, we found close to 10,000 peaks, of which we could assign about half. And then a good 1,000 of those were CF2 peaks, meaning those were PFAS that were actually members of CF2 series. So we have very high confidence that these were actually PFAS. And those were spread over 258 classes. So this is just in one single AFFF sample. And you can see that here in a groundwater sample too, we have more hits, more total peaks. We have less PFAS, but we can still find over 600 PFAS with pretty high confidence here in just one sample, and assign this or spread this over 149 different classes. We also looked at ESI positive. You can see there are way less hits. We can still assign over 1,000 peaks in both cases for the AFFF and the groundwater. For the AFFF, we end up with close to 300 PFAS spread over 84 classes. And this may be quite surprising at first sight. In the groundwater, we were unable to identify any PFAS in positive mode. So these would be zwitterionic and cationic PFAS. And the potential explanation here is that those stick to soil, so that really only the anions make it far away from the source zone where we took the samples. And so you're not finding anything in ESI positive. So the other tool that we use are Kendrick analogous mass difference networks. Because we cannot get isotopes for just any analyte, maybe because they don't include sulfur, for instance, We use the isotopologue identification, or we use the fact that these are members of CF2 chemical mass defect series to identify compounds. And then through these networks, we can basically connect a whole slew of analytes or mass to charge ratios that were detected, and identify a great number of PFAS with high confidence here in one run, basically. And through that, we have identified new PFAS such as polyethoxylated perfluoroalkane sulfonamides. That again is published in the reference that I'll be showing at the end. So then the question is, if we have so many, like hundreds of PFAS identified in just one sample, what do we do with the information? We use data reduction approaches here, such as modified band prevalence diagrams, where we plot the fluorine to carbon ratio as a function of oxygen to carbon ratio. So each and every dot that you're seeing here in this diagram is one PFAS that we have identified. And so these plots then become kind of like a fingerprint for individual samples. I can show this here for 3 examples on this slide. For the aqueous film forming foam on the left, and again, this is just one sample. For a groundwater sample in the middle, and then for a wastewater treatment plant sample on the right-hand side. You can see that these fingerprints differ quite a bit. For the aqueous film forming foam, we have a very wide fluorine to carbon ratio range of less than 0.2 to greater than 2.5, while the oxygen to carbon ratio is smaller. In groundwater, our PFAS have a higher oxygen to carbon ratio, maybe because the ones with lower oxygen content stick to soil more or were transformed. And in wastewater, we also have a low oxygen to carbon ratio, and then a very prominent cluster here too that may be diagnostic in the bottom left of the diagram. So there are different data reduction methods that you could use, and we're really just at the beginning of this journey. I've shown the modified band prevalence diagrams. We do believe that we can use this approach not just for forensic purposes, but also to identify reduction, oxidation, retardation processes along a flow path. At the center of the slide, you see principal component analysis. So here we're trying to cluster and maybe identify different sources. And so at this military installation where we took groundwater samples, the samples that we took on base differed quite a bit from the ones that we saw off base. So just based on the composition here, we would potentially suspect that there are different sources of the PFAS. And then finally, we're looking at overlap between different samples. So let's say between an aqueous film forming foam and wastewater and groundwater. But we're also looking at unique PFAS that occur in these sources so that we can possibly identify marker compounds that can later be analyzed on more widely available low resolution mass spectrometers. So to conclude then, FT-ICRMS is not the silver bullet. It's not going to replace any of the other techniques that are being used. It's really meant to offer an additional line of evidence for these maybe a little more difficult cases where you really have to delve into the weeds for diagnostic purposes, for instance. So FT-ICRMS, as I showed, can detect PFAS that may remain unresolved on other mass spectrometers. And then with these Kendrick analogous mass difference networks, we have ways now where we can identify or assign molecular formulas, elemental formulas to our analytes relatively quickly. And then finally, we can use data reduction approaches, certainly more than I showed here as examples, to do a chemical profiling of our samples, basically a fingerprinting, and use this for source allocation or plume dating or whatever the purpose may be. So as I said, this is what we've done in the first year of the project, and there are 3 more years to come where we will expand the analyses. We will first do a reconnaissance campaign and look at a greater number of AFFF samples, wastewater samples, groundwater samples, to look at product or source specific marker compounds that again can then be analyzed on lower resolution mass spectrometers. We hope to generate additional evidence. What you've seen here were basically just direct infusion results. So the National High Magnetic Field Lab has an LC now, so we can generate chromatographic evidence too. And we can also fragment, and we'll do this in the future, the analytes to get structural information too. And at the end of all this, there will be a PFAS mass spectral library that will be open source for everyone to use. Maybe if we have enough time and resources, we can even get into the NIST in this beautiful NIST format and merge the lists, really just hoping that as many people will use this as possible. So the benefits of the DoD are there's a development of a new analytical method, a new analytical tool. There'll be a comprehensive PFAS library that can be used by not just us or the DoD, but really hopefully by everyone, by scientists and consultants and practitioners. And also forensic marker compounds that you can maybe target in the future a little more easily rather than having to go through non-target analysis each and every time. And so we hope that the products can be used for source attribution, plume dating, and hopefully also to unravel complex fate and transport processes, as I had outlined. So with that, here is the initial publication that came out in 2022, a good year ago, that you can find and read about the details of the work in our first year. And you can see the long list of names already. So this is truly a team effort. And I want to thank all my collaborators here as project PIs in this project. It's Amy McKenna at the National High Magnetic Field Lab, Robert Young at New Mexico State University, and John Kornuk at NAVFAC XWEC. And then we have key team members here, Nassim Pika, who was the first postdoc who basically ventured into the woods here and came up with a lot of the groundwork, how to assign elemental composition here. She's now at Weston. Hamid Sharifan, who was the second postdoc working on this, who optimized the code and was the first one to work on environmental samples. He's at UTEP now. Then there are Juan Chen and Lydia Babcock Adams, who work with Amy McKenna hands-on at the National High Magnetic Field Lab with the instrument. And then there is Wenchao Lu here, my colleague at CSIRO, who is now expanding the code, has made it significantly faster, more streamlined, and is venturing into ESI positive assignments, which is quite a challenge. And so with that, I'm going to leave it here, turn it back to Rula, and would be happy to answer any questions.
Great, thank you so much. We've received a number of questions. We're going to start with one about the ability of FT-ICR-MS to detect PFAS precursors. Is that a capability or not?
So I assume this is polyfluorinated PFAA precursors. Is that correct?
That's a safe guess, yes.
Yeah, so
the question does not specify, but thank you for making the clarification.
Okay, yeah, so yes, so this is a method that you want to use when you really want to identify all these precursor compounds. So this is not something that you would do on a standard basis or to go for, let's say, the list of 40 that are in the method 1633 that can be quantified too. So this is really just for identification. This is not quantitative. We're trying to develop this into a direction where we can get some semi-quantitative information out of it. But this is really about the identification of this, if you will, dark matter. So all these polyfluorinated precursor compounds that could end up as dead-end PFAAs in the end. But that may be so important for us to understand in terms of, you know, what are the different sources, how do these PFAS transport and transform, and possibly also serve as a basis for toxicological studies later on, and focus on, yeah, individual polyfluorinated precursors that with implications.
Great, thank you. How do you avoid false positives when you're doing your PFAS identification efforts? Do you take any steps to avoid this?
Yeah, thank you. So that's a great question. That's one of our biggest concerns when you start with a new analytical method and you develop really a code and a workflow from scratch. The last thing we wanted to do is to assign an elemental composition, a PFAS elemental composition, to a compound that is not a PFAS. So we're not just, as you saw in the number of assignments, we are not just detecting PFAS with this method, we are also detecting natural organic matter, so just background organic carbon. And we don't want to say, oh, this is a PFAS and that's a PFAS when it's really not PFAS. So this is why we are collecting several lines of evidence to give us confidence in our assignments. And a very critical step in there is that we have analyzed and are analyzing a lot of non-PFAS containing samples, so just natural organic matter samples, and then run these PFAS-free, hopefully PFAS-free natural organic matter samples against our PFAS database, and we hope to see no detections. And so the result, and again, you can find that the details in our publication. You can certainly find matches within the ppm error of even 0.2. But what we have not found in natural organic matter are PFAS with more than 2 members within a Kendrick mass defect series. So if we find a series of a CF2 series of PFAS with 3 or more members, we have so far pretty good confidence that these are actually PFAS, and only then we call them out as PFAS with high confidence.
Great, thank you so much. Which other isotopes can be helpful in PFAS identification, and how accurately can you measure their abundance in environmental samples based on your experience, Jens?
Yeah, so I had mentioned sulfur isotopes. Of course, when you have sulfonates and sulfonamides, sulfur is quite abundant in a lot of PFAS, 34 versus 32, so that you can use the 34 sulfur with an abundance of 4.2%. So again, that's known. I had mentioned chlorine, 34 to 35. There is bromine, 79 and 81. And actually, if you do elemental assignment and you look at the chlorine versus bromine isotopes, to tell those apart, you actually need a ppm error of about 2 or less at a mass to charge ratio of around 500, meaning that on a time of flight mass spec, you couldn't really tell them apart. You need at least an orbit trap, or obviously, like ideally an FTICRMS if you have access, to tell those, to say, okay, this is a chlorine-containing compound or it's a bromine-containing PFAS. There are oxygen isotopes that you can look at if your analyte is there in high abundance, because the 18O isotope has an abundance of only about 0.2%. And then you can certainly use carbon-13 isotopes as well to help give you confidence in your elemental composition assignments.
Great, thank you. This is a question from the audience. What is your general opinion on the need of advanced detection methods for PFAS forensics? Do you think that we can only rely on these very high precision techniques to distinguish between sources, or do you believe that standard analysis methods may be sufficient in some cases?
Yeah, that's a super question. I am hoping that we're not going to use this type or any type of high resolution mass spectrometry in each and every case. I think, for once we want to venture deep into the forest here to see what can we do with the instruments that are available to us, and to come back with an answer of how much information is really necessary for forensic purposes to tell sources apart. We are hoping, however, that let's say, a regular, if you will, LC-MS that people use to quantify 40 different PFAS would be enough in a lot of cases. So if you have an electrochemical fluorination AFFF versus a more modern fluorotelmer AFFF, you don't really need any of these instruments. Relative standard analyses will tell you about that difference. And even between products from the same type, often a good tandem mass spectrometry or triple quad mass spectrometry will give you an answer. There are other lines of evidence, for instance, such as branching that you can look at when you use chromatographic methods. So that's something that we haven't looked at here yet. So I think the advantage we have is that we have a great toolkit of several analytical techniques and analytical instruments that we can use, but I really don't envision this to become a standard instrument. That's why we're doing this once, to give us basically the confidence and inform us about how much information is needed, so that in the future we can hopefully do this a little more in a more straightforward fashion.
Great. And one last question for you. Will there be a cost to use the code and the libraries that you are developing, or will it be available for general use?
Yeah, good question. So this will all be open source. Some of it is published already. Again, this was a 1-year or 15-month limited scope project. I would refer you here to the project website. You can see the SERDP project number here, ER20-1265. You can Google that and get to the project website. So there's a phase 1 final report published already with a preliminary database. There are also all the spectra are made available on the Open Science Framework, and you can find that information in the publication. So all of this will be open source, and we're really hoping that people use this as widely as possible, and we'll certainly also try to reach out to NIST and try to consolidate these databases or the information that we're all collecting as well as we can.
Wonderful. Thank you so much, Jens. We're going to get back to you with one more question, but I wanted to pull Jared back into the discussion and relay one question that we didn't get to initially from ExxonMobil. Jared, have you broken down the database that you're developing based on industry, or is that not attached to the data that you've included in the database?
So right now, the only information that we've captured to date is sample category. And so that would be things like, was the sample an AFFF, a commercial formulation, et cetera. The annotations that are available in DIMSpec can be expanded. So we would be able to provide categories of interest, but we have not broken that down by industry as of yet, no.
Great. Thank you so much, Jared. And Jens, just to kind of wrap up with you also, what are the next steps, if any, for your work? And are there any takeaway messages you want to reinforce before we wrap up?
Yeah, so as I had kind of shown on our previous slide, the next steps are really, we do have some method development left to do, especially the assignment of ESI positive species, so the cations and zwitterions. That's not trivial. That's something that we're working on. The code is in pretty good shape, I'd say. So we're really looking forward to analyzing. We really have to develop QA/QC too. So there are fundamental questions such as how well do you have to clean the instrument between injections, because it's really a completely new method. So all of these are outcomes of the research project too. But ultimately, of course, we want to get to samples and test this on a broad range. So that's the goal. And yeah, that's so take-home messages. Maybe stay tuned. This was the first year. There are 3 more exciting years to come. And yeah, look forward to hearing more from our study. Thank you.
Thank you, Jens, and thank you again, Jared. Both of you did an outstanding job. A reminder to all of you that on the line that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer them in the future. Our next webinar is coming up in January. The topic will involve PFAS. It'll be on PFAS leaching models and long-term monitoring, and it will feature 2 speakers, Dr. Gao from the University of Arizona and Ms. Beckley from GSA Environmental. So make sure to check our webinar webpage next week to register for this and other webinars in 2024. Thank you again for joining us. And if you have a few moments and can take a minute to complete the survey that will pop up on your screen, we would really appreciate it. This concludes today's webcast. Thank you for joining us.